some.
I was particularly confused with 3.6. Just looking at it.
Um, So one of the things about this is just, I think this is trying to illustrate, is just, first of all, that there are ideals in effects that are ideals in the effects that are not principal. So that's so consider, I'll call it evaluation. Evaluation. Effects. Now, it's certainly the case that this homomorphism could have zero basis. Could be injected. It's possible. In this case, well, okay, it's principal, it's generated by zero. So we just, that's it. Generator is zero. So let's assume none. Assume none. And let f of x and we also maybe want to make an assumption on, well, okay. I want to say something else, which I haven't defined, but what would have defined? We've gotten a little farther in, which was I want to say that f of x is also primitive. Let's also assume primitive. You might can look in the book, but I'll tell you what it is. Means coefficients are relatively prime well, there's no single prime number that divides all the coefficients. And we can turn this off. That sounds fun. So you should ask, like, why why do we know that we can find such a thing? Why, why can we find something that's both a minimal degree and primitive in this kernel? And the answer to that, well, you guys tell me. Complex.
The leading coefficient rate constant, but
That's not so important.
um, I think primitive just means that it's coefficient for
More or less.
and I'm sorry, if you, so if you can pick out a relatively the 19 just like the prime numbers of cell. What does that mean? Like, I just going to make relative prime.
What about this? What does it mean for F? So let's say we can certainly choose something of smallest degree, right?
Right.
Okay, so let's choose something of smallest degree. And it's in the kernel. And let's assume it's not. Right? Let's say, so this can be, you can choose this. If G of X B in kernel. And what does it mean? Then it means that G of alpha equals 0, right? If that's one, that being in the kernel means G of alpha equals 0. Now, what if it's not? What if it's not permanent? That means that okay, if the leading coefficient is negative, you just multiply by negative. That's not a problem. But the bigger issue is like, what if there's a prime that factors all of the coefficients? What do you do? What if G is, for instance, like an example, don't write this on your homework. Let's explain. But G is like 16 x squared minus 8x plus 32. I know when I put alpha in, I get 0.
You can just divide everything by 8.
Exactly. That's right. You can just divide everything by 8 and it's still in the kernel, right?
And then
Because
it's primitive.
yeah. So you divide by the greatest common divisor of everything, and it's still in the kernel. G alpha will still be 0. Dividing the is a primitive. Now the claim is, if we find such an F, then the ideal kernel is in fact generated by this F. Claim that for this claim, I urge you look in this section, find a few things. One thing is, okay, so let's all explain. So if G of X element of the kernel, then this is kind of what this section does. It deals with the interplay between polynomials with rational coefficients and polynomials with integer coefficients. I was going to say, okay, well, let's say we have a G of X here, and we can consider g of x is a polynomial in Q, Q. An element. Q x. Why is that? What's that? Thing?
Dan,
Dan?
is that what it said? Or is it saying that? Or thus?
Dan.
Dan, okay.
You write it this way, because it's a little confusing. I mean, this is the principal ideal. I don't know if that's. Why is it true? Alex, this does not require section 3. It requires sections 1 and 2. That'll be covered in this. So let me ask this thing. You guys, what's your feelings about this guy? How do you feel about like feeling emotional reactions to hate all of them? If I say, okay, what do you think of Z of X? The thing about Z of X is actually, honestly, you like do it. You've been playing with it, working with it for so long, you've forgotten, you've taken it for granted. You take Z of X for granted. Almost like all these problems you write down. Yeah, people hate writing fractions, so they always write down factor polynomials in high school. The best cases are when they're integers. I'm working with this for a long time, but it's actually quite a complicated thing. This, from a perspective of mathematics, is much better. What is this? What kind of ring is this? I'll set 3 answers.
Like PID.
PID. It's a Euclidean domain too.
Yeah.
This is a field. This is not a field. You have coefficients in a field, life is glorious. It's so easy. It's a Euclidean domain. It's the best of all things that you could ever hope for in your life. Rings, commuter rings. It's, I mean, the only thing simpler than that is like a field. Right? That's which is where everything goes right. Like Euclidean domains are really great. You can do anything you want. Anything. Anyway, so this is a good place to be. This is a harder place. Because this is definitely not a field. It's not a horrible ring, but it's actually quite a complicated ring. Very, very complicated. All number 3. So now, what I'm saying is that when I consider, okay, so I've got now, of course, there is this containment. you want to do some interplay. I have I have F, that's in here. I have G, which is also. But since they're both in here, I can consider them as elements in here. When I do that, I can say, okay, well, G of X is in the kernel of X. And what I definitely know to be true is that these things are equal if I consider them in this. I just right. This is a PID. The kernel is a principal ID. And I found something in that kernel that's of minimal degree. That has to be the gen. Whether it's primitive or not, I can, because I'm in Q of X, I can multiply by a fraction. So this is true in that's why this is true. Because PX is not a PID. Definitely not a PID. Or two dimensional. Maybe like one. Okay. But now, as we know this is true, we have that G of X equal to F of X times H of X for some H of X in now these two guys, they're both in integers. They both have integer coefficients because this is here and this is chosen to be. There's a proposition in this section 3 which says there's a unique way of taking a rational polynomial and writing it as a fraction times a primitive. Unique way. Look it up in that section. So this is equal to f of x times c times what they call h naught of x, or h naught. Now, we may as well assume that G is primitive, right? Because if G is not primitive, then we can do what we did before. We can say G is, you know, the least common multiple times some G prime or some G tilde, which is primitive. And G tilde would have to be number. So we can replace G by the primitive part of G. Let's assume G is primitive. So we should start with that. But now you use this lemma that's in the book, proposition. It says that this is unique. You have a rational polynomial, it's uniquely written as a rational times primitive. Which means that this, since it's primitive, is like 1 times that. Means that this rational, actually you need to use 2. There are 2 things in the book you need. One is you need this uniqueness. The other is you need that if you have 2 primitives, you multiply them together, it's a primitive. We state this. So since products of primitives are primitives, this product f of x times h naught of x is a primitive. But now we have the uniqueness. By uniqueness, g of x equals c plus c. Because this is 1 times g. That's, I take a primitive, what is the unique fraction times it that's, of that form? It's 1 times it. So we have 2 different ways of writing rational times primitive. Since they're both the same, rational numbers must be both. But now we have 2, these are both primitives. This is saying exactly what we wanted. So g of x is in it's an ideal in the integers, and the ring polynomial. So it's principle. So that is the polynomial that will generate. It's the smallest degree polynomial that is primitive, for which alpha is a root. There's a word for that, that if it were monic, the word for that would be that this is the minimal polynomial of alpha. And this leads into a whole bunch of field theory. So it's kind of like foreshadowing, much more than that. All right, so what else? The other one, so this is 3.6. Remember what was the other one from chapter 2?
3.2.
The 2 integer polynomials are relatively prime elements, 2x, if and only if the ideal they generate d of x to be an integer. I'll be there. This actually, I think you could do this without reading any of this section. I think. You do need to kind of do what I just did. Not to involve a lot of separate sections. Do one of the things. Okay, so let me ask you guys all of you guys. What do you do with relatively prime things? What have we done many times with relatively prime? Basically, I hear relatively prime, I immediately think of that form. Like it's so useful, why wouldn't I think? However, that's 2 things in ZX. That's not given. So in the existence of that stuff doesn't make sense. But we can do what we did a second ago. Say, okay, look, this is contained in there. Consider them as all. Is a PID. You have a notion, based on the divisor, and all of the things that want. True. 2. Let's assume we'll go 1. Okay, so assume that's relatively prime. Okay, well, what do I say? say Bezier. Exists. What? You. Rational. What's that? That's polynomials. Second.
Sorry, I was thinking to myself before speaking aloud.
Okay. What's Bezier say? Bezier. F of x. Oh, you know, you're thinking of the division algorithm. Okay, two equations. Like A equals B times Q plus R. Another equation like AR plus BS equals D. This is like division algorithm. But that's what you use to get this one. The Euclidean algorithm to get this kind of state. Here D is equal to you can say for it, but when it's relatively prime, that means it's. So this is the Bezier kind of thing, and I think Bezier really is meant for PIDs. Officially, they call this something else than free. So anyway, I got this PX, FX, this QX, my R and S are at P and Q. PX is 1. Probably Browning's greatest common divisor is 1. Give E greatest common. Right? What do I do now, Mary? Good.
I want to show that the ideal it generates is in a contained
Yep.
Just restating the problem.
Good to see that's a good thing to do. Calling for time. I'm stalling.
Oh.
What do you think? Come on, guys. What are elements of the? What's that?
Now I'm thinking about California.
It's a great state.
I mean, obviously, one. I feel like it's like some sort of observation you have to make because I don't think that there's much you can do otherwise.
What is first? What is the ideal they generate? What does that mean? How do you get the idea? You have two elements. We have one element, ideal it generates is its principal ideal. All multiples of that. So you have two elements. What are the elements of the ideal two elements? What do they look like? The sum of what? Not just the two generators. Remember, you have to be able to multiply by elements of the ring. So if I have an A and a B, B in a ring, R. I want to know what the ideal generated by A and B is. I mean, the sums of all multiples. So it looks like something like this, something kind of familiar.
There's a linear combination.
Yep. Well, kind of linear, but I don't, you just, all combinations. Linear is space. Here we're taking elements of the ring. Right? This is what it is. Okay, does that look familiar? Say F and G, you're looking at the ideal of things that F and G generate. It's like this, right? One is an integer, but what is the problem? You're right, one is an integer. But what is the problem? Why can't I just say that? So one is in the ideal they generate? Is that what you're saying? Is that what you're saying?
We're saying,
Hold on. You can read very carefully. We want to be very, very cautious. Two integer polynomials are relatively prime in a ring of rational, and only if ideal they generate in integers. Was R here? This. Are P and Q, are they in Z of X? Q of X. One is not necessarily. I need these to be in Z of X. What do?
multiply by like this here,
Multiply by what?
by something.
By what? How do I, okay, what do you, you're right, multiply it by what? Multiply the whole equation by, you look at P and Q, the coefficients are all rational, right? They're rational numbers. Something over something else. So what do you want to do? You want to clear denominators. Take the product of all the denominators of all the coefficients of P and Q. So multiply by that. That'll clear all the denominators out. Now you have two integer polynomials. On the other side, you've got some big number, but it's an integer. Right? It'll take, I don't know, what do you want to call it? 10? So take n. You can say that these common multiple, let's just say the product. Denominators. Coefficients of P and Q. By n equals an n. Ideal generator. What about the converse? This was an if and only if statement. So here we assume they're relatively prime, and we obtain an integer in the ideal they generate. What if there's an integer in the ideal they generate? How do we show they're relatively prime? Firstly, and it's an element. Well, I don't know, let's say H and K. Integer. That's that. definition of the ideal generated by these two elements. So we can do kind of the opposite way. Again, that means that they're relatively fine. You take it, if you, what is the greatest common divisor? It's the element whose principal ideal is the sum of the two ideals. So one is in that sum. That means that whole ring is the sum of. Okay. I'm feeling good. Someone's gonna say yes at some.
You can't.
My kids don't. They do exactly what your parents son.
It was more of a chuckle.
You know? Problems. Right here.
Only 3 other problems.
But yeah, so maybe one more. We look at one. Raw polynomials are like it's a ring in between, field of fractions of polynomials and the original. It's actually what you call localization. So, and you can show that this statement holds for any localization. Nice. Anyway, that's not. What do you guys think?
Figure out the definition of polynomials and how.
Laurent polynomials?
It says they're linear, finite linear combinations of powers of t, negative exponent.
Positive. Like a polynomial, but you let your exponent be negative integers. So like you've seen like t, this is a great one. My favorite polynomial. Great polynomial. The homological linear potential to sphere. Mirror. Symmetry. I've spent a lot of my life thinking about Laurent polynomials. A lot of wonder. So, 3 things. What do you think?
Just to clarify, the longer is the equilibrium cell. full ideal domain.
The goal is to show that you have an ideal in this ring that it's principal. When you want to, I mean, okay. Is it a domain? Yes, it's a domain. Why is it a domain? Well, if you, the point is if you had a zero divisor, you could see that it would have to be, you can multiply any of the wrong polynomials by power of x to get a polynomial. Just take your state's lowest exponent is like x to the negative 100. By x to the 100. Everything becomes a polynomial. So if you have a product of two Laurent polynomials equal to 0, then by multiplying by the power of x, the product of two polynomials equal to 0. That doesn't happen. Polynomials form a domain. So it's a domain. Don't worry about it. So the real thing is to show it's a principal ideal domain. So that any ideal is principal. I'll start with an ideal. Give yourself a little notation, right? So that's I be an ideal. I'll show there's. What do you know is a PID? What are some examples of PID? Integers? Integers form a PID. Something kind of like this, but not. Pretty hard.
Calculus, integers, so like,
No. Okay, maybe. But those aren't domains. Well, unless they're fields. But okay. So, what else? What's an example of a PID? We just looked at. Rationals are fields, but not rationals. But what? Rationals, but blah with blah. Rational blah. But it's on the screen. Rational. Thank you. There you
Okay.
go. There's no flaws. This is right. But does it need to be rational? I need to have rationals here. Could I put something else? Like reals or C? What else could I put? He will not get a. He's not a. Good. I need a field. Okay, guys, you got to look back at the notes. Come on. Everyone's losing track here. This is a PID. This is a Euclidean domain, which is a PID. This is like there are two main, like all of the Euclidean domains are sort of strongest, satisfy the best properties we could ask for a ring. Short of being a field. So our main examples would be the most typical examples would be the integers and polynomials over a single coefficients. Other examples that we looked at were like Gaussian integers. We looked at more, but these are kind of the ones we jump so far. These are the ones you want to look to for good properties, where you have greatest common divisors, where you can do like Bezoos theorem, for all the things that we believe want are there. this optically looks a lot like this, right? It's close, not quite, but it's contained in there, right? I mean, all polynomials are also Laurent polynomials, they just don't have x's with negative exponents. So I can do something, I can intersect. That's J equal this. What's J? J is ideal. Ideal, good job.
I can count the letters before I guessed.
Yeah, there you go. Ideal of fx. And what did we just say about these sets? They are unique. Whatever this is, so you can prove that really easy. It's not hard. So J is generated by a single. You're hunting to show that this is a principal ideal domain. You found a single element from that ideal. So then you claim that in fact I equals. Now, this is a little confusing because I just said J was equal to that. But here I'm talking about this. Here I'm saying this in fx. Here this is. Different rings. Okay, so here's a hint of how to prove this, but I won't do it. Help us wrong. I did like to say something. And threaten to quit. If you have, it's sort of what I was saying before about the if you have an element in I, and you want to show it's in this fx, you can get it into the polynomial by multiplying by a suitable power of x. So if it's in I, h of x is in I, then x to some power is in I intersect fx. X to some power times it is a multiple of f of x. Once you have that, you can undo that multiplication. Because you got the polynomials. Sense? All right, guys, I think I'm gonna wrap up on that. So, but I haven't gotten back to you yet. I got